I am going to show you a previous video last time on this channel. That's a joke. Okay, this is a program I made. I added a little bit, but it won't change the way it runs. This is some spacecraft orbiting the Earth. And I went over the details of this in super simple code and made it as simple as possible. So now what I want to do is say, well, what if I replace the spacecraft with the moon? Can we do that? And the answer is yes, we can. But it's going to lead to some really interesting things that happen. Okay. And you may think spacecraft orbiting the Earth, moon orbiting the Earth, what's the difference? Difference will be seen. Trust me. It's going to be great. Okay. Let's review real quick. I'm going to briefly review what we did here, and then I'm going to do that to the moon. I'm just going to change the spacecraft to moon. That's all I'm going to do, and I'm going to show you that it's wrong. Okay. So let's go back over here to the paper and let's talk about really briefly. I tried to draw this as accurately as I can. I just guessed. Here's the Earth. There's the moon. They're really far apart compared to their size. You never draw them that way in pictures because it looks dumb. But it's true. We're going to make it real. We're going to make a real Earth-Moon system. We can do that in Python. So remember that if I want to, I have two things. We did the same thing before. I have the position of the Earth. I call that RE. I have the position of the moon. This marker seems to be doing not so well. And then the position from the Earth to the moon. That's the vector R. And so R is equal to the position of the moon minus the position of the Earth. And you can put the Earth at the origin if you want. It doesn't really matter. But it's important to do this step in case that's not true. Hint, spoiler alert, it's not going to be true. We're going to make it not true. It's going to be awesome. So with that, I can use the gravitational force to calculate the force on the moon. I'm just calling it F. So it's negative G. This is just the gravitational constant, the product of the mass of the Earth and the mass of the moon, this magnitude squared, and then you have to multiply it by a unit vector in that direction to get this force. If you don't do that, then you just get a force, and it doesn't take into account that as the moon moves over here, the force is in a different direction. So you do have to do that, and that's what makes this awesome. Now, if this starts with some momentum P1, I can use the momentum principle. I'm going through this super quick. I do it in much more detail in the previous video. If I don't link to that, you can find it on my channel, hopefully. And so if I take a short time interval delta t, I can assume that force is constant and use that to find the new momentum. So I could solve this for P2. P2 is P1. Well, that's like that. I'll write it down here. P2 is equal to P1 plus F delta t. That's the momentum update formula. And then we can do a similar thing for position using this momentum that we just calculated. This gives me the average velocity. I take the position of the moon, not R, right? I need the position of the moon. That's R, M. M stands for the moon. 1 at the beginning of the time interval. I can find the position at the end of the time interval, and I just do the same thing over and over and over again. So all I'm going to do right now is to change this to the moon. So I have this Earth-Moon distance, I call it REM, not the band. And then I do know the period T is like 29 days or something like that. I have the actual number already in the code. I looked it up. This is the synodic period. This is how long it takes to make a circle, not to orbit the Earth, because the Earth moves too. But now I'm thinking I should use sidereal. So I should use the other version. I'll look that up because I'm ignoring the interaction with the sun. So the Earth's actually not moving. So I do want to find the period around the Earth, not the period. I don't want to take in. Should I even talk about this? So here's the sun, here's the Earth, here's the moon. And as the Earth orbits the sun and the moon orbits it, it has to go further around to get back to the same location with respect to the Earth. And that's the synodic. The synodic is longer, right? The synodic, I'm getting this confused. You know what? I'm just going to use the sidereal, and I'm going to be done with that. It may be wrong, because I haven't thought it through, and that's my fault. Okay, so but what I'm going to do, if once I know the period, I can say this is equal to 2 pi rem. No, it's going to be the velocity is the distance around 2 pi rem, right, to go around once divided by the period. I need that velocity to find this value right here. So I'm going to put this on the x-axis, and it's going to move in the y direction. And I'm not going to have the Earth rotate in the right direction, and I'm fine with that. Okay. Let's jump over to the code. We just got to make some changes. We don't really have to do much, okay? Jumping back, this is the program. The only thing, and I did change it, right? I added some things in here. I added this stuff right there. And that's the synodic period, and I'm going to change that to sidereal period, which I'm still not quite sure about. But it's fine. The physics is all the same. It's 27.321 days. So if I multiply that by 24 hours, and then I multiply that by 3,600 seconds per hour, then it'll give me the period in seconds. I know that's not the best way to do it, but all my other stuff is in meters and kilograms and seconds, so I want that in meters and kilograms and seconds. Let's just go ahead and calculate V0. Like I said, it was 2 times pi times REM. So I have all these values. I have the gravitational constant, the mass of the Earth, the radius of the Earth, the Earth-Moon distance, the radius of the Moon, the mass of the Moon, the period, and this will be the velocity, so it would be divided by t. And this RE max, that's just because it's not in a circle. I might use that. This is the angular tilt. I don't know if I'm going to use that. So I'm just going to go through here. I'm going to change craft to moon. Oops. Moon, it's a sphere. Its position, let's put the Earth at the origin. It doesn't really matter. Gonna do it. Its position for this one, it's gonna be REM 0, 0. It's on the x-axis. And the radius is gonna be RM. And the color is not gonna be yellow. It's not a yellow moon. It's not made of cheese. Never was. And then we'll just leave it. The default color is white, so I'm going to leave it like that because it looks like a moon. Now, the momentum, I'm going to change this to the moon. You need to be careful about modifying programs because you may miss a word somewhere, and that's fine. And I'm probably going to mass of the moon, and this is going to be what I call V0. So now it's moving in the y direction just like that. Let's put the dt as larger. Let's say I'm going to go with 30 seconds. I don't know if that's good. I don't need this. Let's do this for while t is less than t, 1 period. That should work, right? Rate 1000, I'm going to leave that. R is moon.pos. And this will be G times mm. Moon.p. Moon.p. And this is not the cool part. There will be a cool part. Moon.pos. And you can tell I'm not doing this beforehand, right? I just looked up those values. So it's all live. It's all real. All performed live before a live audience, even though it's not. And I don't need to print that. Okay, let's see if this actually works. Not 100% sure it will. Okay, something happened. What the heck happened? Oh no, it's moving. Where's the Earth? Let's make this go slower. Huh. That's weird. Okay, let's do while t is less than 0. So it won't run the loop. Let's just see if it makes the two objects. Okay, there's my Earth. That's good. And there's my moon right there. Do you see that? So you see there's your real Earth-Moon distance. I must have the wrong velocity. 2 pi r divided by t. T is 27 days times 24 hours times 3,600. That seems right. Masses are right. Mass of the moon. radius dt r. Let's do this for 1,000 seconds. Let's see what happens. And let's print. I don't know what's going wrong. Let's print just moon dot p divided by mm. I want the velocity. And let's up here, let's print v0. Let's see, print v0 vo. v0 equals v0. Let's just print it. Let's just do that. Okay, so something weird's happening. It's like blowing up. v0 is 1,000. Okay, that seems okay. If I look up here, I'm looking on the Wikipedia page. Orbital speed is 1 kilometer per second. That's right. See, but it like, what's the final position? Position, R-E-M, R-E-M, that's right. Radius, make trail. Let's print the position. Print moon POS equals moon.pos. It looks like it's just blowing up. Yeah, so it blew up. It went times 10 to the 25th. That's not where it should be. Why did it blow up? Okay, so everything's good, I think, before I got to the loop. R equals moon.pos minus earth.pos. F equals g mass moon norm r squared. Moon.p equals moon.p.pos. Moon.pos equals... Aha! See? What did I say? I said, you got to be careful. And so I did this on purpose. I said, you got to be careful when you just take existing code and modify it, because something bad's going to happen. Now, I'm going to go ahead. I know that's my mistake. I'm going to change that back to T, and I know it's going to work. If it doesn't work, I'm just going to be sad. Okay. So it's moving, I think. It's just, I forgot I got this rate down, so let's put this at 5. And this is probably too small of a time step, and we'll change that. Yeah. If I'm running at 5,000, then it's just too slow. I'm doing too many calculations. And we can make a larger calculation and a smaller rate. It should be fine. But it looks like it's working, right? There's my Earth-Moon orbit right there, and it's pretty cool, and we're going to make it better. So let me fix this real quick. So let's say dt is 100, and then I'm going to change this to 1,000. So it's 100 seconds, and then 1,000 frames per second. Yeah, okay. So we're all cool, right? Everything's cool. Everything's not cool. This is broken. This does not work. I'm going to show you why. Let's go up here and add a graph. G1 equals graph. Title equals Earth Moon. X title equals time. Let's just do time. T in seconds, which is stupid, I know. And then let's do for the other axis, I'm going to plot Y title equals P in kilogram meters per second. I'm going to plot momentum. And I can't plot the whole thing, so I'm going to plot actually X momentum. Width equals 400. Height, let's spell it right. Height equals 200. Now, that's my labels. The actual graph I need to put as another curve. So let's call this FM for the moon. It's a G curve. Color equals color.blue. So it's a blue moon. Get it? Okay. So down here, I want to plot on that. I'm going to plot let's plot the X momentum as a function of time. So it starts off with a 0x momentum, but over time, yeah, let's just do that. So fm.plot t moon.p.x. That's the X momentum. Let's just see what happens. So that's orbiting. And so, like I said, it started at 0. Now it has a negative momentum. It's going to go back. But something's not right here. And the thing that's not right is that if this is true, why is the momentum changing at all? How do you change the momentum of an object? You have a force. But if I have an Earth-Moon system, the center of mass and the momentum of the center of mass should be stationary if there's no external forces, which I don't have. And so the problem here is that I didn't take into account the change in momentum of the Earth. So let's go back to the paper and fix this thing. Okay, new sheet of paper. So here is my Earth, and here is my moon, not to scale. And I calculated this force on there, F. And this has a momentum, so I get a change in momentum of the moon, delta P moon, over some time interval. But forces come in pairs. So that means that there's a force pulling on the moon, on the Earth, the same magnitude of that. And the moon will have an equal and opposite change in momentum. So I need to take into account the momentum of the moon. Now, I'm going to make it wrong and then fix it, okay? But that means that the Earth's going to move. Now, maybe the Earth doesn't move much, and that's fine. But let's still add that in there anyway. So it's actually not too difficult to do. Let's go back to the computer. I'm going to do this. I'm doing this wrong, okay, as a learning tool. So I have the momentum of the moon. Let's just say the Earth's momentum is Earth dot P, and let's put that at mass of the Earth times vector 0, 0, 0. Let's say it's big. Let's put it at rest. That's fine. Up here, I'm going to plot FE equals G curve color equals color dot red. And so we can plot the momentum of the Earth, and then I can say FT equals G curve color equals color dot purple. And this will be the total. I'll put a label. Label equals total momentum. Okay. So I've got the Earth's momentum right there. Now I can change that. So right here, I calculate R, I calculate F. How do I calculate the force on the moon? On the moon to the Earth. I could redo the calculation, but I don't have to, because it's the opposite of this. So if I want to update the Earth's momentum, Earth.P equals Earth.P minus F times dt. So minus F is the force on the Earth, right? I don't really need to recalculate it. I already did it. It's just the minus of that. Now I can update the position of the Earth, Earth.pos, Earth.pos, plus Earth.p times dt divided by mass of the Earth. That's all I need to do. Well, I do want to plot this. So let's say Fe.plot t Earth.p.x. I'm just doing the x components. And then ft.plot is t, and then the sum of these two. So it's going to be earth.p.x plus moon.p.x. Let's run this thing and see what happens. Okay, so it's orbiting. I don't see the Earth doing anything, so it must be fine. Let's run it all the way through. Let's check the graphs, see how the graphs are doing. Okay, this looks kind of good, right? Because now you'll see that it looks like the momentum is 0. Okay, that's fine. And because they're doing equal and opposite change. This is momentum. It's not velocity, right? So that's actually a pretty good graph. I'm pretty happy with that graph. But I wanted to get all the way back to the beginning. And I should have increased my rate because I'm so impatient. Here we go. Here we go. There we go. So it kind of is not quite on top of each other. Let's plot the trajectory of the Earth just for fun. So I'm not going to change the labels on the code here. I'm just going to take that off. I'm going to take that off, and let's plot Earth.pos.x versus Earth.pos.y. Let's just see if the Earth does indeed move. Did I anger it? What did I do? Hello? It's not running at all. Okay, let's see. Did I ever save this? No, save. Okay, it should still work. Let's try running it again. Maybe it's just the internet. Okay, there it goes. Okay, I don't care about that. I care about this. And you can see right here that the Earth does indeed move. Look at this. The moon's moving in the positive direction, and so is the Earth. They're both moving up. Okay, but it does indeed move. If you plotted the center of mass of this whole system, which I'm not going to do, if you did, you would see that the center of mass is constantly moving up. Okay, let's see if we can see that. I'm going to do the following. I'm going to increase my time step even more. I'm going to increase this even more. And then I'm going to make the Earth have a trail. Make trail equals true. And then let's let this run for 3 orbits. Okay, so it's going a lot faster. There you go. You can see the motion of the Earth moving, and it's moving up like that. The whole thing's moving up, right? Which isn't wrong. It's not wrong. It's just that that's not what I want. If I want that to stay stationary, I can fix this. All I need to do is say the momentum of the whole system is 0. And if I want to do that, I just set this. Let's get rid of this stuff. I'm going to comment that out and say that's equal to negative moon.p. So if I do that, the moon's momentum and the Earth's momentum added together are 0, so the center of mass is stationary, and it's not going to go anywhere. So they're not the same velocity, they're the same momentum. The total momentum is 0 now. So if I do this again, the Earth still moves. You can see it doing a little circle like that, but it stays in the same place. Okay, so we have built our imperfect Earth-Moon system. I do want to do one thing. It's not super great, but I kind of like it. We can make this look a little bit more realistic. I'm going to do 2 things. Number 1, I'm going to make it doesn't really help because they're so far away, but I'm going to make the Earth and the Moon not shiny. So I can do that. I really don't even think it's worth it here because they're so tiny to see. I'm going to go up here for the Earth. Let's put a return here, so I can do that. Make trail equals true. Shininess equals 0. So right now, when there's an external light and it shines on the system and it's shiny, but the Earth's not really shiny. Kind of it is. It just makes it look better. Same thing is true for the moon. Let's say the moon shininess equals 0. So that is a property. If I run that, you probably won't see much of a difference, but it does look. I don't even want to do this now. I'm not going to do it. I was going to put it so there's actually multiple lights in the animation, and I was going to change it to 1 light, but you can't see the Earth that much. I don't think it's worth it. Also, the Earth does not cast a shadow. Okay, so if you want to try to do this to show lunar eclipses or solar eclipses, you can't. It just doesn't. They don't cast shadows in this thing. You could artificially make it, probably, but okay. So that's it. The important thing is if we want to go from the spacecraft orbiting the Earth to the moon, we have to also include that the Earth moves because of the force due to the moon. That we didn't do that with the spacecraft because if it had a mass of 5,000 kilograms, the change in momentum of the moon and the Earth is still the same as the spacecraft. It just that when you divide by the mass of the Earth, you get a stupid small number, and you wouldn't notice it's moving. But when you have a larger object like the Earth and the moon does indeed make the Earth move. Okay, so maybe we'll do the Earth, Moon, Sun system later, but for now, I'll stop with this. I was going to also include the non-circular orbit. It's not completely circular. It's fine. We can do that later and show some cool stuff with it, but I think this is good. I'm going to put the link to this code down below, and don't forget the previous video if you want to look at that.